Hello everyone, Dr. White back with a small series of screencasts on section 4.3 of our textbook, Binomial Distribution. So at the beginning of a new topic, we always take a look at our studio, kind of clean things up. So in the upper left, I notice I have a file open, looks like my DA from section 4.1. I've already, done that work and don't need it anymore, so I'll close out this little buffer. Don't worry, the file still exists in your submit folder. You can always open it again. My global environment is empty. That's good. If yours isn't, I'd say push the broom and say yes, and you'll empty out your global environment. In the Files pane, I'm looking into my submit folder. I think I'll click on my home, and good place to start. Okay, we want to pick up the slides. So let's go to ... /com. Enter. Dr. White stuff. Mat 111. Slides. Navigate down to OS-4.3 Binomial Distribution Slides. View in web browser. There they are. The title on this is wrong. It should just say binomial distribution, but I'll fix that by the time you see these slides. So packages I need today, Tiger Stats. All right, let me make sure I've got that attached. So I say library Tiger Stats. There it is, loading up. Okay. Binomial random variables. So there's a certain chance process situation that gives rise to binomial random variables, and I'll just call it the binomial situation. You need to learn what this situation is by definition before you can learn about the concept of binomial random variables. So suppose four things. Suppose you perform a specific number of trials that we will call n. So 10 trials, 20 trials, 170 trials, whatever, but a specific fixed number. And each trial has two outcomes, either success or failure. In your given situation, success and failure can mean different things, but only two outcomes are allowed on each trial. There's a chance of success on every trial, and that chance of success we'll call little p, and it needs to be the same on each trial. And the fourth thing that makes a situation a binomial situation is that the outcome of any one trial does not affect the outcome of any other trial. So this means that the trials are independent of each other. If you have those four situations, you've got the binomial situation. And let's say that in that situation, you decide to count the number of successes that you get in your n trials. Call it capital X. So let's let capital X be the number of successes in your n trials. Capital X is called a binomial random variable. Binomial, bi comes from the Greek for two, nom comes from the Greek for name, two names, success and failure, the two outcomes on each trial. Mathematically, for short and symbolism, we'll write things like this: X twiddles binom NP. That is saying that X has the distribution, that's more or less what the twiddles means, of a binomial with n trials and chance p of success. Or if you'd like to say X is distributed as binomial with n trials and chance p of success on each trial. So we need some examples to clear this up. And we also need some non-examples, and that will help sharpen our ability to tell whether or not we're in a situation that meets the definition of binomial. So for example, let's let x equal the number of heads that you get in 3 flips of a fair coin. We've looked at this random variable before. It's a binomial random variable, but why? Well, we've got to argue why all 4 conditions for a binomial situation exist here. Well, first of all, the thing about there being a specific number of trials. Well, you can think of every flip of the coin as a trial. 3 flips, so n is 3. Next, there needs to be 2 outcomes for each trial. And there are heads and tails. We're just going to call heads success and tails failure. You could switch it around, and that's still okay for the binomial situation. Doesn't matter which thing you're counting as your success. There just have to be 2 outcomes, though, for every trial. And finally, what's the probability of success? Is that the same on every trial? Well, the probability of success now is 0.5 because it's a fair coin. And that's the same on every flip. That chance does not change from one flip to another. That's what makes it binomial. The 0.5 is not what's making it binomial. The same on each flip is what's making it binomial. And finally, the outcomes of the trials have to be independent of each other. Well, that's true. The outcomes of the flips don't affect each other. If I get heads on the first flip, that doesn't mean I somehow have to get tails on the second flip to balance it out or anything like that. The coin has no memory and no conscience. What came before doesn't affect what comes later. So we've got all 4 situations. Fixed number of trials, 2 outcomes on each trial, same chance of success on each trial, and the trials are independent of each other. So counting the number of heads was a binomial. Here's another example of a binomial random variable. Say you're in a situation where you're shooting free throws, and let's say that you can make 70% of the free throw shots that you attempt. Let's also say that your shots don't affect each other. So it's like just because you make one shot doesn't mean that you get overconfident and not make the next one, or you make one shot and you feel more relaxed and so you do better on the next ones. Let's just say that doesn't happen. And let's say you go to the line and you take 20 shots. You're in a binomial situation here. If you let y be the number of shots you make, so you can think about making a shot as a success and not making it as a failure, you're counting up the number of successes, so you've got yourself a binomial random variable. Y is distributed as binomial with 20 trials, and 0.7 is your chance of success on each trial. So let's see if we can make R try out some binomial random variables. So let's model the situation of a 70% free throw shooter taking 20 free throws and counting up how many shots she makes. This can be done with an R function called R binom. R for random, binom for binomial random variable. The second input here, size is 20, says how many trials. The third input, prob equals 0.7, says what's the chance of success. The 1 says that I just want to take my 20 shots and count the successes once. I don't want to do it more than once. So let's give it a try. Copy, head to our studio. I'll make a little bigger for you. Paste, run. And so this time I got 12 out of 20. 12 out of 20 is 60%. I'm a 70% free throw shooter by my skill level. So, just by chance variation, I did a little worse than that this time. Let me try it again. I'm going to up arrow and run again. And so like the next time I tried 20 shots, I got 15 out of 20. That's 75%. So that's a little bit better than my, expected 70%. Let's try it again. And I got 15 again. If you'd like to try it lots of times, you could just do this. I'm up arrowing and I'm going to say, how about like 10 days in a row, I go and take 20 shots each day. So let me put a 10 here at the beginning. And there's the way it came out for my 10 days. Okay. Back to the slides. In this next bit of code, I'm modeling the situation of flipping a fair coin 100 times. Size is 100 is how many trials. Prob is 0.5 is the 50% chance of heads. I'm only going to flip 100 times once, so I'm saying a 1 here. And so when I tried this, when making the slides, I got 48 heads and 100 flips. I guess you would expect about 50 heads per 100 flips, give or take some for chance error, so 48 doesn't look that unusual. Why don't you try it in RStudio and see what you get for yourself. Here's yet another example of a binomial random variable. Go all the way back to dolphin communication at the beginning of the course. Remember, Buzz the dolphin was put in this situation where he had to choose a button to push, possibly with some help from Doris, right? She was squeaking at him, trying to tell him which was the right button. And he does that 16 times. That's his trials. N is 16. And every time he's either going to get the correct button that gets him a fish or not. So there's success and failure, 2 outcomes each trial. And each time his chance of getting it right is some unknown chance called P. I don't know what that chance is. Skeptics who think that Buzz can't communicate with Doris at all think that that chance is 0.5, that he's just randomly guessing the buttons. But folks who thought that dolphins could communicate think that that number P is higher than 0.5. And I'm also assuming, with what grounds I don't really quite know, that his tries don't affect each other. That if he gets a fish on one trial, that doesn't mean that he really doesn't want any more fish later on, and that he tries to push the wrong button or anything like that. That on each try, whatever happens is not affected by what came before and won't affect what comes after. If all those 4 things are true, then we've got ourselves another binomial random variable here, z, the number of times he pushes the correct button. Z is distributed as binomial with 16 trials and unknown chance P of success. And that's the whole mystery, isn't it? The unknown chance, and the whole inferential situation in the dolphin communication scenario turned around this question. Was Buzz just guessing randomly? Then P would be 0.5. But maybe he could communicate with Doris to some extent, in which case P was bigger than 0.5. And we tried to use the data to decide which of those 2 options is really the more sensible one. Now for some non-examples of binomial random variables. Say a kindergarten class has 20 children, okay? Maybe you could think of each child as a trial, and what you're doing when you look at each child is to see whether or not the child is going to get the flu this winter. And say that you just happen to know from epidemiological research that throughout the country, 10% of all kindergarten children this year get the flu. And so you can figure, well, each child has a 0.10 chance of getting the flu. And you let Z be the number of children in this class of 20 children who will get the flu this winter. This is so close to being a binomial random variable. It's got the fixed trials, it's got the two outcomes, and it's got this fixed chance of success on each trial, but what it lacks is the independence. Even though each kid has a 10% chance of getting the flu, once you know one child has the flu, then that really increases your estimate of the chances that another child in the same class is going to get the flu. So there's a lack of independence between the trials. Not a binomial random variable. Here's one that I would ask you to just stop and practice for a little bit before you go on to the next slide, see the answer. So you choose 20 people at random. They're not related to each other. And you ask each person how many brothers or sisters he or she has. And you let X be the total number of brothers reported. So what you're doing is you're going to each person and you say, how many brothers do you have? And the person maybe says 2. You go to the next person, how many brothers do you have? And the person says 0. And you go to the next person, how many brothers do you have? And the person says 5, and so on. And you add up those numbers, those 20 numbers. Is X binomial? If so, what's the number of trials? What's the chance of success, P? So think about it for a bit. Well, the answer is that X is not binomial. There is a fixed number of trials, 20. And the trials don't affect each other, because the people are not related. So like knowing that one person has 3 brothers is not going to tell you anything about how many brothers, this other person has. But the big problem here is that there's not just 2 outcomes on each trial, because the outcomes are 0, 1, 2, 3, 4 on up, because those are the possible answers that a person could give to the question, how many brothers do you have? Without just 2 outcomes, you can't even have the same chance of success on each outcome. You're blown. Let's try this one. You sample 71 people at random from a large population. You record the sex of each person, male or female. And let's say we just happen to know that 55% of the population is female. You don't have to know it. Suppose it's just true, whether or not you know it, that 55% of the population is female. And you count up the total number of females in the sample. Is that binomial? And if so, what's the N and what's the P? Think about that for a moment. Well, this one I think is binomial. There's a fixed number of trials because you can think of each person sampled as a trial. And so your fixed number of trials is the 71 people, 71. Each trial has 2 outcomes because the person can be male or female. Now we're thinking about counting up the number of females in the sample, so we should set success to be female and failure to be male. Now let's think about the chance of success on each trial. Is it the same from one trial to another? Well, 55% of this population is female. Every time I pull out a person, 55% chance female. Now, I'm assuming here that it's a really, really large population compared to just the 71 that I'm picking out of it. Because actually, when you do pull a female out of a population, you slightly reduce the proportion of females in what's left, And you don't put her back in and give yourself, a chance to get her again. That would be kind of useless information in a situation like this. So you really are leaving her out, not replacing her, and slightly changing the proportion of females. But if it's a really, really large population and you pull one female out, the change in the proportion is basically nil. And so this thing here is essentially true. The chance is essentially 55% on each of your 71 trials. So I'm going to give myself a pass and say that's right. And the trials are independent because you're picking randomly from the population. And so when you pick one person and find out that person is female, it doesn't tell you anything about the next person you pick because that person's going to be picked randomly out of everybody else. So I'm saying we got binomial here. Number of trials is 71. Chance of success on each trial is 0.55. Okay, that's it for now. We've defined binomial random variables, but now we need to think more how to learn their distribution so that we can answer probability questions about them. That'll show in the next screencast.